Chem 100. This is material for exam 9. Right? That's not a 0. Exam 90. That's exam 9. There's a hole in the board. Chapter 8 of your textbook covers redox reactions and electrochemistry. So let's share the PowerPoints and learn some electrochemistry. Here we go. Now, and let's make a slideshow out of it. Here we go. Okay. We've already done gases. We just finished acids and bases. Now we're ready for redox reactions. And of course, energy is not on the menu for this class. So what are some topics that we're going to cover? Well, of course, oxidation reduction reactions. And we're going to learn how to balance equations based upon a redox method. And then we'll learn a little bit about electrochemistry and the various types of reactions that it describes. So what is an oxidation reduction reaction? It's often abbreviated redox, simply because ox-red doesn't sound right. If we use the same order, oxidation reduction, it just wouldn't click. So oxidation reduction reactions are often called redox, and they always involve the transfer of electrons from one reactant to the other. And here's an example. If you take sodium metal and react it with chlorine gas, you get a transfer of electrons from the metal to the non-metal, which is typical. It's not always that obvious, but when you have this situation, the metals tend to lose their electrons, the non-metals tend to gain electrons, and that's what's happening here. And when you do that transfer, you find out that a transfer of a single electron from one atom of sodium makes a sodium +1 ion and a chlorine +1 ion. Notice also that in the process, this bond between the two chlorine atoms had to be broken. And there was another type of bond between the sodiums, it's called a metallic bond, that also had to be broken. So you can see the transfer of electrons there. Oxidation is the descriptive term for loss of electrons. So when something is oxidized, it has to lose electrons, which means sodium was oxidized. And then the chlorine gained electrons, which is in chemical terms called reduction. So chlorine gained electron, it was reduced. Sodium lost electron, it was oxidized. Now, how do you remember that? Well, there's a little mnemonic. On this slide, I've got a little better presentation for remembering the process. It's called oil rig, right? Just remember oil rig. Oxidation is loss. Reduction is gain. And that refers to the electrons. So oxidation is loss of electrons. Reduction is gain of electrons. So let's look at an example. Here we have a tin 2+ ion, and we have iron 3+ ion. And you know which one lost electrons and which one gained electrons by the outcome. What are the products? Notice that here, tin now is 4+ instead of 2+. So what had to happen in order to go from this to this? Remember, the balance of charge in an atom or an ion is due to electron movement. not protons. So you don't go from here to here by adding protons, which are positively charged. You go from here to here by losing two negatives. Lose two electrons, you get a 4+. So what does that mean? Oxidation is loss. So 10 was oxidized. Okay? Another important point to make is that whenever an oxidation takes place, a reduction always accompanies it. They occur in pairs. You never have one without the other. So in this case, if 10 2+ was oxidized, then iron 3+ had to be reduced. And we see that's true. 3+ to 2+ charge means each iron atom, each iron ion had to gain an electron. And the electron came from 10. All right. Now there's another concept. It's an important skill. It's a bookkeeping scheme for keeping track of electrons, right? It's called oxidation state. So we determine the oxidation state of each of the reactants in our reaction, and each of the products in the reaction, and by assigning an oxidation state to each one of those components, we can tell which one lost electrons and which one gained electrons during the reaction. So these are the rules for oxidation state. For an atom that is in its elemental state, its oxidation state is always 0. So for that previous example, sodium, as the metal, the solid metal at room temperature and pressure, would be an oxidation state of 0. And sometimes you write it up here in the upper right-hand corner, just like we would for a charge. Remember when we were earlier, we were describing those 4 positions around a symbol, right? This would be charge. And now we're also using that space for the oxidation state. Okay. Sometimes it is a charge, but it doesn't have to be a charge. This is a bookkeeping scheme for tracking electron movement. And then, of course, the chlorine that is its normal elemental state, the diatomic. And its oxidation state is also 0. Now, when we say 0 here, we mean 0 for each chlorine in that molecule. Okay? So those would be 0. The ions, right, if we let the reaction proceed, then this is going to produce ions, 2 of these and 2 of those. Let's see, 2 and 2, 2 and 2. Yes. In this case, when you have an element, an atom that's an ion, its oxidation state is the charge. So that would be a +1. This would be a -1 oxidation state. So those are easy. But if you have an element that's buried in a compound, a covalent compound, then the oxidation states have to be assigned. And the first one that we assign is oxygen. If oxygen is in a covalent compound, which means what? It's bound to another nonmetal. Right? then its oxidation state is -2. Right? So carbon dioxide, the oxidation state here would be assumed to be a 2-. Right? Now, the only exception to that rule is when oxygen is bound to itself in a peroxide. So anytime you have a peroxide of any kind, the oxidation state of oxygen is -1. And this illustration is there to show you that if this oxygen is a -1 and that oxygen is a -1, then overall that group is a -2. So that's a -1, -1, -1, -1, -1, -1 for any of those peroxide types. Now, what does the R mean? The R is a placeholder. The R could be anything. It could be any non-metal or group with a non-metal connection. All right, so there's the next rule for oxygen. Hydrogen in a covalent compound is always taken as +1. Perfect example is water. This will be a +1, correct? So what's the total? Well, you've got 2 of them. So you have a +2 oxidation state for all of the hydrogens in that molecule, which means that we have to balance the charge, balance the oxidation state for this molecule. That means oxygen has to be a -2. So there, even by calculation, the oxygen then meets the standard that we've established in rule number 3. And this is only covalent compounds. There are situations where hydrogen can take on a -1 oxidation state. But in those cases, it has to be bound to a metal. Those are the hydrides, like, for instance, lithium hydride. Right? That brings us to the next rule. Well, no, the rule after that. Fluorine is always taken as -1 when it's in a compound. Whether it's bound to a metal or a non-metal, it doesn't matter. It's always taken as -1. The sum of the oxidation states for a neutral compound must be 0. So here we have an example. The sum, where you have +1 times 2 is +2, is balanced by -2. That one satisfied rule number 6. Its oxidation state sum is 0. So for this one, what would that be? What would carbon have to be in order to give us a 0 summation? Well, 2 times a -2 is 4 minuses. There's only one carbon, so it has to balance the entire oxidation state by itself. That means +4 is the carbon oxidation state. That's a calculated based on what we are following in the rules. Then we can calculate the rest of them. If we have an ion, the same thing. Now, let's see. Hold on a second. I keep up with my hard copy. Right. Okay, the last rule. The last rule, I'll come back to lithium hydride in a minute. The sum of the oxidation states for a neutral compound is 0. For an ion, the sum of the oxidation states is the charge on the ion. So I got a perfect example. There's the carbonate ion, right? Sodium carbonate, potassium carbonate. That's a polyatomic ion, right? So the sum of the oxidation states for this ion must be the 2- charge. So what's oxygen? Oxygen has to be a -2. Right? -2 times 3 is -6. Correct? Okay? So how do you get a -2 out of a -6 with an oxidation state for carbon? Carbon has to be a +4. That gives you a -2. Okay? Now, if you're trying to determine carbon, there's another way. It's actually the same way. It's just a different way of thinking about it. So here's what I do. If I want to determine what's left over, then I say, okay, I'm going to reserve 2 of those minuses for the charge. Then what's left over has to be balanced by carbon. So if I reserve those 2, well, make it a plus to neutralize. Then you have a -4. That has to be balanced by carbon +4. That's the way I think about it. And it works very well for me. If it doesn't work for you, use some other way. But in the end, the total of all the oxidation states must be a 2- for this polyatomic ion. The last rule, alkali metals, group number 1, right? Group number 1, they're always +1. And group number 2, alkaline earths, they're always +2. Okay, so if that's the case, then for this compound, lithium is a +1. So what does hydrogen have to be? In that case, hydrogen is a -1. So in that case, we start from the metal and work to the nonmetal. There are other cases where we probably could add another rule. Aluminum is always +3. I don't know of aluminum in any situation where it's not +3. It might be in some occasions, but they're rare. But these are hard and fast. Alkali metals are +1, alkaline earths are +2. All right. So let's take some examples and see if we can calculate them based on those rules. Right? So here we have a situation where we want to find the oxidation state for each of the elements in the compound or the ion. We've already done carbonate. So when we get to that one, we'll just skip over it. Okay, what is this compound? That is the dichromate ion. It has a 2- charge for the entire ion. That means that it has to be balanced by 2 pluses for potassium. So it's a balanced ionic compound. There's the cation, there's the anion. But we want to find out what's the oxidation state for each one. Well, the rules say potassium is always +1, correct? It's an alkali metal. And oxygen this is not a peroxide, so this one is -2. So now what we have to do is calculate what is chromium. Well, everything has to add up to 0 because this is a neutral compound. So how many pluses do you have? You have 2 pluses here. Over here you have 14 minuses, right? So what charge needs to be balanced by the chromium? Well, add that one to this one and you get a -12, correct? -12. So that means both of these together, those 2 chromiums have to be 12 plus. So what is individual? There are 2 of them, so each one is plus 6. Okay? There you go. Now, I said I was going to skip this one because we've already done it. Right? We already determined that one. Now we're going to go to manganese dioxide. All right. Notice for the first one, chromium is an alkaline, is a transition metal, excuse me. Transition metals. Transition metals are notorious for having multiple possible charges. The same holds true for this manganese dioxide. Manganese could have several different possible charges, right, in this compound, different oxidation states. So it stands to reason that we need to calculate that one. We know what this one is, right? It's -2. Both of them together are -4, correct? So with one manganese balancing off -4 to give you a 0 total, this one has to be +4. Okay, it's the only possibility. Simple math. How about this one? PCl5. All right, we didn't cover that rule. But when you have a halogen combined with some other nonmetal, then you go for the halogen first. So in this case, we're going to have to say that chlorine is the same as fluorine. It's a -1 charge, or oxidation state, I should say. So that means you have -5 here. That means this one has to be a +5. Okay? If we don't do it that way, then there's no way to calculate the oxidation states. And it's important to remember that oxidation state isn't necessarily charge. Oxidation state is a bookkeeping method for following the electron movements. How about SF4? This one is easier because we have a rule for fluorine. Fluorine is always -1, right? There's some cases where chlorine is different. And I'll show you one of those in a minute. Let me see. Do we have one on a slide for that? I'll do that one before we leave this slide. But let's get this one out of the way. SF4, right? If fluorine is -1, based on our rules, then the total is -4. That means sulfur has to be +4. Okay? There you go. Now, a case where chlorine can assume different oxidation states. And this holds for bromine and iodine also. Fluorine is the only halogen that has a fixed oxidation state. It never changes. But there are cases where chlorine, bromine, iodine could have various oxidation states. And all you have to do is look at the periodic table that I've given you, and you'll find multiple values there in the little square with each of those halogens. All right, so my example is going to be the polyatomic ions with chlorine and oxygen. Remember when we were naming these things? I always start with this one, the chlorate ion. We could also have only 2 oxygens, the chlorite ion, or the hypochlorite ion. And then we could also have the perchlorate ion. Now, where do you start? In this case, we peg oxygen to a -2 oxidation state and calculate the chlorine. Okay, so if oxygen is -2 in each one of these, then let's put chlorine here and oxygen there. So we're going to do oxygen down here total. Okay, total for each one of these. Okay. So the total oxygen here is 2 minus times 4 is 8 minus, correct? This one would be 3 times 2 would be 6 minus. This one would be 4 minus, and this would be 2 minus. Okay, that's the total oxygen that has to be balanced. Well, you need to keep one of these out for the negative. So you really only need to balance 7 here, right? So we need to balance 7 minuses, 5 minuses, 3 minuses, and 1 minus, because we have to maintain that negative charge. So we held one of them out for the charge. Now we only have to balance this with a positive. One chlorine has to bear the brunt. It has to cover the entire positive balance for that. So this chlorine would be 7 plus, this one would be 5 plus, 3 plus, and 1 plus. So those are the oxidation states for chlorine in that series of polyatomic ions. This also can explain why the acid of each one is different strength. Right? The strength of the acid goes like this. If we add a hydrogen here, 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 get rid of the negative. The oxidation state hasn't changed. It's the same. But with this higher oxidation state, what does that mean? That bigger positive charge is pulling the electrons much stronger. So this hydrogen is being depleted of more electron density than these. Okay, so that means that it's easier to remove this hydrogen because it's lost a lot of electron density to that chlorine at a higher oxidation state. And then this is lesser, lesser, lesser. The hydrogen now can retain more of its electron density and becomes more difficult to separate it from the polyatomic ion. So that's why the strength decreases this way, increases that way. All right, so let's move to the next slide. Let's see how we doing. Yeah, that's centered okay. All right, next slide. Here's our previous example. Sodium reacts with chlorine gas. By the way, this reaction is extremely exothermic. It gives off a lot of heat. Probably some light too when the reaction gets going. It's very energetic. So what are the oxidation states? We did this one earlier actually. Right? So we know that these are elemental. Their oxidation states are 0. How about sodium chloride? Well, they're going to be the charges. That has to be a +1. This has to be a -1. There's no two ways about it. By rule and by calculation, the sodium is an alkali metal. So it has to be +1. That means chlorine has to be -1. Okay? Which one is oxidized? Oxidation, oil, is loss. Sodium loses an electron, which means it is oxidized. All right, let's write this up here. 2 sodiums with an oxidation state of 0 and chlorine gas with an oxidation state of 0 yields sodium plus and chlorine minus. Okay. Oh, it put them in there. These are sodium chloride as the solid, but I wanted to show the ions. This is together is sodium chloride solid. Okay. So you'll have table salt after this reaction in the reaction vessel. And I wouldn't advise it, but if you were allowed to taste it, it would taste salty. Okay, in this case, which one is oxidized? This one is oxidized because it loses an electron. Sometimes I write it this way. Loss, 1 electron per sodium times 2 equals 2 electrons. Right? And this has to be 2. And this has to be 2. Okay? So if sodium is oxidized, and remember, oxidation and reduction always go together. So sodium now is considered the reducing agent. In other words, it causes the reduction of chlorine. So it is the reduction agent. Right there. So if chlorine is reduced, right, it had to go from here over to here for a gain 1 electron per chlorine times 2 equals 2 electrons. So if this one is reduced, it is the oxidizing agent. I wrote that wrong. It's not the reduction. Reducing agent. This one is the oxidizing agent. Okay? Those are just some. That's just some terminology that you need to be need to store in your brain. All right, so let's take this example and analyze it for oxidation, reduction, and the movement of electrons. Notice that 2 electrons here gained were lost here. That always has, in a balanced equation, that has to equal that every time. There's no compromise. If that doesn't happen, then your equation is not balanced. Or you've done some miscalculation somewhere. Okay. So let's see. Let me reach that out of there. Get the rest of it. All right, so here's our example. CH4, that's methane, right? Natural gas. Plus 2 O2s, and this equation is supposed to be balanced. We can check it. And we have carbon dioxide plus 2 water. Okay. Now, the first thing you do with an equation like this is determine the oxidation states for every element. All right? So we know that in a covalent compound, hydrogen is going to be +1. That's given. This one is an element, so it's 0. This one is in a compound, so it's -2. Right? This one is in a compound, it's -2. We did water before, and we know this hydrogen is +1. Right? So we need to calculate the rest of them. Let's go back over here. So this is a total of +4, correct? For hydrogen. So that means carbon has to be a -4. Okay? How about this carbon? Well, 2 times a -2 is what? -4. So that means this carbon has to be +4. All right, so now we have all the oxidation states. Carbon is oxidized. It goes from, it loses electrons. It goes from a -4 to a +4. So it loses electrons. We know that qualitatively. How many did it lose? Right? If we do this, like that, loss, what? How many electrons did carbon have to lose to go from -4 to +4? Well, from a -4 to 0 would be 4 electrons, correct? But from 0 to +4 would be another 4. So it actually lost 8 electrons per carbon. Times 1 equals 8 electrons total. Okay? So carbon is oxidized. That means it's the reducing agent. It provides electrons to somebody to be reduced. And that somebody is oxygen. Look, oxygen goes from a 0 to a -2 here and a -2 there. In that case, you got oxygen going into 2 compounds. Fortunately, for our calculations, they're both the same. They're both the same oxidation state. So you would go here, there, and you would go here, there. So you would gain how many electrons per oxygen? To go from 0 to -2 is 2 electrons. 2 electrons per oxygen. Times how many oxygens are there? Well, there are 2 here, right? 2 times 1, and there are 2 here. So that's 4 equals 8 electrons. So notice 8 and 8 balance. So we do have a balanced equation. Oxygen is reduced. That makes it the oxidizing agent. It facilitates the oxidation of carbon. That's what that means. And there are the calculations. All right, so this slide is just a review of what we've come across so far. Oops, sorry, Corky. All right. Always be sure my board's not walking away on me. Okay, so what have we learned so far? Redox is a transfer of electrons. That's foundational. That's definition. When you transfer those electrons, you could form ions. You don't have to, but you could form ions. The oxidation is by definition the loss of electrons, right? OIL, oil. That makes anything that is oxidized a reducing agent, while reduction is the gain of electrons. RIG, reduction is gain. In that case, you have reduced something and it becomes the oxidizing agent. Now, your textbook and a lot of textbooks speak of oxidation state as increasing or decreasing. What they mean by that is if the oxidation state increases, it becomes more positive. So it could go from a -4 to a -2. That's increasing oxidation state. Okay, that's what that means. Or it could go from a 0 to a +7. Right, that's an increase. From 0 to +7 is an increase in oxidation state. For reduction, you just go the other direction, right? Reduction would be this way. You would decrease your oxidation state. You'd get more negative. That's what those statements mean. Okay. Another concept check. Let's see. Okay, we've got 3 reactions coming up, written out, and we need to determine which of these reactions are actually redox reactions, oxidation reduction. And then identify we need to identify the oxidizing, the reduction and the oxidation in order to answer the first question. And then with that information, we can decide which one is the oxidizing agent, which one's the reducing agent. Okay, so here they are, these 3 equations. So we have zinc, solid, plus hydrochloric acid yields zinc chloride. Oh, that's in solution, sorry. Plus hydrogen gas. Okay? Now here's a trick. Whenever you have an element on one side of the equation and you find it in a compound on the other side as a product, that is always oxidation reduction, without fail. Or if you go the other direction, if you have an element in the products, but it came from a reactant in which it was a member of a compound, that also signifies oxidation reduction. Okay, so now we can determine, that's the shorthand way, the quick way. You know that answer. If the question is, which is oxidation reduction, you can get that one quick. If you see that relationship, you know it's redox. But this one is 0, and this one is 0. They're both elemental. For this one, chlorine is -1, hydrogen is +1. Right? Simple. This one, chlorine is -1. So that means 2 minuses have to be balanced by zinc. That's 2+. Okay? So we've got all of this, our oxidation states identified. And I didn't leave myself room on top, so I'm going to have to do it down here. So what happens here? All right. What did we have to do? Increasing oxidation state. We had to lose electrons. Loss. 2 electrons per zinc times 1 equals 2 electrons. Okay? So if that is the loss, if that is the oxidation, which makes it what? This is the reducing agent. Right there. So that means we're going from +1 to 0 for hydrogen. There's your reduction, right? +1 to 0 is a decrease in oxidation state. We have added electrons. So we need to go like this. There. Okay. So a gain of what? 1 electron per hydrogen times 2 equals 2 electrons. So we're balanced here and here. This is a gain. So hydrogen is reduced, which makes it the oxidizing agent. Okay? And there it is in animated PowerPoint form. That is an oxidation reduction reaction. And there's your oxidizing, your reducing agent, right, in red. See that red right there, that red circle. This blue circle is the oxidizing agent. Okay, how about the next one? So I'm going to have to erase this one. Okay, this one's a long one. I'm going to have to start way over here on the left. So there's our dichromate ion. Notice anything funny about this one? You got an anion and an anion reacting. Right? Charges don't balance. So this is a net reaction. We've left out the spectators. There was a cation attached to this one, I'm sure, which doesn't do anything. And this one also has a cation that is a spectator. So we're only interested in the species that are actually involved in the reaction. Okay, so let's write it up here. Dichromate ion. So this is B, dichromate. Then we're going to react it with 2 hydroxyls. And it's going to produce a chromate ion. And water. Okay. So I suspect this is balanced. We can add them up, right? 7 oxygens here, 2 there is 9. And here we have 8 plus 1 is 9. Right? 2 chromiums here, 2 chromiums there. And hydrogens, 2 hydrogens here and 2 hydrogens there. So it should be balanced. Let's find out whether it's an oxidation reduction reaction, though. I mean, the temptation is to just say, yeah, it is, because of all these charge changes. But the only way to know for sure, since we don't have that rule or that trick that I gave you on the first one, then we have to actually calculate the oxidation states for all the atoms in this reaction and determine if there is oxidation and reduction. All right, so oxygen is going to be 2 minus each. Times 7 is minus 14. We need to hold 1 out for that charge. That means, wait a minute, I did something wrong. 2 times 7 is 14. Oh, sorry. I knew something was wrong. 12. We need to hold 2 negatives out. So that means we have to balance 12. That means this is plus 12, and each one is plus 6. Okay? For this one, oxygen is minus 2, hydrogen is plus 1, and plus 1 and a minus 2 is a negative. So that's correct. Minus 2 and a plus 1 for hydrogen. Over here we have 4 times 2, 4 times 2 minus here is 8 minus for oxygen. And we hold 2 of those out. So we have to balance a 6 plus with 1 chromium, right? So nothing happened to the chromium, right? It's plus 6 and plus 6. How about over here? This is 2 minus and this is +1. Right? So the hydrogens didn't change, the oxygens didn't change, the chromiums didn't change oxidation states. This is not a redox reaction. Okay? Now let's look at the last one. Let's see, here we go. I can put this one over here. See, we've got 2 copper 1 chloride in aqueous solution, and by some change, it reacts and produces this one, copper 2 chloride, plus copper solid metal. Okay? So, what's strange about this reaction? You've only got one reactant over here. Well, actually, you have 2. You got this one and this one, both of them. One of them does one thing and one of them does the other. Right? You got one copper goes here and the other copper goes there. So our rule, our trick from the first one holds. You got a compound here with copper and it's an element over here. That is oxidation reduction without fail. But that's not the only thing happening in this reaction. Let's do the oxidation states. Chlorine is -1. That's where we start with this one. So that means this one has to be +1. Copper is 0 here. But copper here is +2. That's 2 minuses balanced by +2. So one of these coppers, in fact, you can write it this way. Like that. One of these coppers goes to here. Right? Going from a +1 to a +2, any increase in oxidation state means we lose electrons. Loss, 1 electron per copper. Okay? This one, this copper goes here. It gained an electron. Right? Gain 1 electron per copper. So they're balanced. All right. Which one is the, well, this is an oxidation reduction reaction, obviously. There you go, there you go, there you go. Now, which one is, if this one is oxidized, that means it is the reducing agent. Right? So there it is. That's the reducing agent. But this one is reduced. So it's the oxidizing agent. They're both. One of them is the reducing agent, the other one's the oxidizing agent. This is a special type of reaction called a disproportionation reaction. All right. So let's go and learn a method for balancing equations by redox methods. Right? If your reaction is a redox reaction, remember, up till now, we only know one way to balance equations. You just use my budgeting scheme. And very often that'll work. In some cases, it's difficult to make it work. And those cases are not invariably, but very often, oxidation reduction reactions. So we've got another method that helps balance the equations using what we know about oxidation and reduction. All right, so let's go to the next slide. It's called the method of half reactions. So what do? The first thing we do is identify the oxidation states for all of the elements in the given reaction. And then we split it into two. We split it into a reduction reaction and an oxidation reaction. So here's our example. We've got 8 hydrogens, protons, so this is probably acidic solution, reacted with the manganate ion and the iron 2 ion, yields manganese 2+ ion, iron 3+ ion, and water. Right? So let's split that into two. Right? We need to know the oxidation states first. Right? These ions are easy. Their oxidation state is the charge. Okay. Then what? Well, oxygen in this compound is going to be considered 2- or -2 only. So that means manganese, well, there's another oxygen, excuse me. That means manganese has to be a +7, right? Because 4 times 2- is 8, 8-. We reserve 1- for the charge. That means 7- have to be balanced with a 7+. And then all we have left is this hydrogen. It's +1. Okay, so what is the reduction reaction? What's the oxidizing reaction? The reduction reaction is the one in which we have added electrons to manganese to go from a +7 to a +2. That's 5 electrons each. That one in there and that one in there, right? But notice that in order to balance a half reaction, the same rules apply. You've got to have all the elements there for the reactants and the products. So the oxygen is there. We need oxygen. There it is. But now we've added hydrogen, right? So now we need hydrogen there. So those need to be added. Now, normally when you do this process, you don't have the coefficients to go on. In fact, oftentimes you don't have the hydrogens and you don't have the waters there. You just have this compound, that ion, and that ion, and you work from there. And I'm going to show you how to do that. This is a demonstration of just splitting into two, reduction and oxidation. We'll refine the technique in just a minute. Right? And we know that 5 electrons were transferred. So if the electrons were added to manganese, that means the electrons have to be reactants. And now these 5 electrons are buried in the manganese with that charge. On the other hand, we go from iron, which is oxidized, to iron 3+. And how many electrons did it lose to get there? Well, it lost 1 electron per iron, but there are 5 of them. So there are your 5 electrons. Notice that the same number of electrons that go into this half reaction as reactants are the same number that come out of this reaction as products. So there you also have a balance. Okay, so there's an example of splitting a reaction, a balanced equation actually, into 2 half reactions. Now let's look at the method that we would encounter in the real world. Okay, I got a set of rules. Yeah, set of rules first. And we'll go through these rather quickly because the only way to learn rules is to actually work problems using those rules. So the first thing you do, you write the equations. You take what's given to you as reactants and products, and then you assign oxidation states to each of the elements and decide which one is the oxidation, which one is the reduction half reaction. That's the first point. Then you separate them into their half reactions. One for reduction, one for oxidation. Then you go into each one and you be sure that all the elements are balanced except for hydrogen and oxygen. Right? They come in separate steps later. If there is no hydrogen or oxygen, you just balance the elements. If there are hydrogen and oxygen in your half reaction, then you leave them alone for this step. Right? For each of the half reactions, you balance the elements first. Then you balance the oxygens. If there are any oxygens in there, you balance the oxygens by adding water. So if you have oxygen on the reactant side, you'll put water on the product side to balance the oxygens on each side. And vice versa. If your product has oxygen in it and your reactant doesn't, then you put water on the reactant side. Now, after you do that, that's going to give you some hydrogens that you didn't have before. So you balance the hydrogens with protons, right? The H+ ion. Now, I emphasize that this method is for acidic solutions. Right? It's possible to have reactions in basic solution, but we're going to do acidic solution first. So there's your acid that balances the hydrogens. Then at the end, once you've got all of these other things balanced, then you balance the electrons. You make sure that the number of electrons that are transferred in the reaction are balanced for each individual reaction. So they may not be the same at this stage. You might have 2 electrons added in one reaction and 6 electrons subtracted in the other reaction. Then you cannot add those 2 reactions back together to give you the full, complete, balanced equation until the electrons are balanced. So if you have a different number of electrons in one reaction than the other one, you have to correct that by multiplying the entire equation, oxidation equation, reaction equation, as the case may be, by some whole number in order to make all the electrons balanced. Then you can add them back together. And once you've added them back together, you cancel out identical species in numbers for what's left over. And then you check to be sure that your balancing is kosher. All right. So here's an example. We've got, in this reaction, we do have a dichromate ion that becomes, remember what this one was? 6+. We calculated that earlier, 6+, going to 3+. So the chromium did change in this one. In this one, sulfur is going from one state to another state. We have to decide what are their oxidation states and which one is reduced, which one is oxidized. Okay. Now, separate into half reactions. We actually skipped a step. We need to determine the oxidation states for each one. Then you can separate them. So we're doing 2 things at once here. Right? This chromium went from +6 to +3. So it was reduced. We added electrons. Correct? Okay, so we balance the elements. I think I've got my animations out of order. I apologize for that. 2 chromiums here, 2 chromiums there. Okay, simple. Do we have any oxygens that need to be balanced? Well, yeah, we do. Let's see, are we getting these out of order? Yes, we are. We're not supposed to do the electrons yet. I don't think it'll affect the results, but it's just out of order from the rules I gave you. All right. So in the next slide, we're going to balance. Here we go. I think the order that the addition of electrons occurs is not important because we're not balancing them yet. So for this one, we need to balance oxygen. So which side does the water go on? It goes over here. So there's your water. So how many of these oxygens do we need? Well, we got 7 over here, so we need 7 over here. Right? Okay. Now what did we do? Well, we added extra hydrogens. Right? We added 14 hydrogens. So to balance those hydrogens, they need to go over here on the reactant side. I guess we're going to do waters first. Sorry. So here we have an oxygen, 3, that makes 4 oxygens. Okay, now we got the oxygens balanced. Let's do hydrogens. Here we go. So now we add 14 hydrogens over here. Okay, now for the next one, we added 1 water here, so we need 2 hydrogens on the product side, right? 2 hydrogens from water, 2 hydrogens there. Okay, now we should have balanced all the elements, oxygens, and hydrogens. So what's next? Now we need to make the electrons line up. So there we have 6 electrons on this side and only 2 on that side. So the easiest way is to increase the second reaction with a multiplier. Multiply it by 3. There we go. Now we'll add these 2 equations together. All right. Now, do you see anything that can be canceled? Oh, forgot the electrons. Yeah, you can cancel these electrons. Notice that when we write the balanced equation, the electrons aren't there. They're not considered part of the reaction when we write them because they cancel out. Right? They're necessary to balance the equation, but to write the finished equation, there are no electrons explicitly in that reaction equation. What else can we do? Well, those don't cancel. That's a sulfite and a sulfate. Chromium's okay. Hydrogens, I don't see anything over here to cancel. Oh, we have waters on both sides. So these 3 waters cancel 3 of those and leave 4 behind as product. Like that. Oh, we did balance hydrogens also. So waters and hydrogens need to be, we do some canceling there. So these 6 cancel 6 of those and leaves 8. So here are 8 hydrogens as reactants and 4 waters as product. Right. So that equation is balanced. Oops, sorry. That equation is balanced in acidic conditions. Right? There are your protons. That means it's acid. Okay? Hold that thought. I'm going to tell you how to balance basic solutions in just a minute. But we're going to have a look at a different equation, I think. Yes. Actually, several of them. Yeah, I've got about 1, 2, 3, 4 more slides, and then we get to a discussion of basic solutions in balancing equations. This is the method for acidic. And by the way, I might add, when you balance an equation for basic conditions, I call it the fake acid method. You do the acid balance first, and then you convert it to basic. So that's just a teaser. All right, so let's look at this one. Cerium 2+ ion and cobalt 2+ yields cerium 3+ and cobalt. Is that right? Cobalt metal. Okay. What's the coefficient in front of this term right here? Okay. So, all right, it doesn't give you an explicit, it does do, excuse me, the oxidation states are easy because these are all charged single element ions. That's a 2+, that's a 2+, this is a 3+, and that's a 0. Right, so that's 0. There's a 3+, there's a 2+, there's a 2+. Okay, so which one is reduced? For this type of reaction, you don't need to split it into half reactions. I'm going to show you a shortcut method for the less complicated types. Okay, so this one is 0, that's 3+, 2+, 2+. All right, look at this cobalt. Cobalt is going from 2+ to 0, which is what? Reduction. So here we have gain 2 electrons per cobalt. Here we have oxidation. So we loss 1 electron per cerium. Okay? So what's the easiest way to balance this equation is make sure you have the same number of electrons transferred. This one's 2, that one needs to be 2. So times what? 2. So 2 times here and here will give you 2 electrons, right? So that equation is probably balanced. So the coefficient in front of the cerium 2+ is 2. So we didn't even have to break it into half reactions. All right. I am burning up in here. I'm going to have to reduce the temperature. There we go. That's much better. Plus, I'm going to turn this little fan right in my face. Okay. So that was simple, right? We had no hydrogens here, no oxygens to deal with. Half reaction method would have been overkill. You can still do it, and that's no problem. But we actually did the half reaction, only we didn't separate them physically. We just did the half reactions in place. And that's a quicker way. So if you need a quicker way on a test, then that's a good way to go. Okay, now this one, where you have an oxygen in here, we probably should separate these into individuals, half reactions. Okay, So I'm going to do this one on the board. And the slide is complete, right? It'll give you everything that I'm putting on the board. But if I talk and write at the same time, it may make more sense. It'll definitely take more time, which might be helpful also. This stuff takes a little time to soak in. So we'll take our time about it since we're good. We got till noon. Okay, here's our parent reaction. Bromine ion plus manganate ion yields bromine liquid plus manganese 2 plus ion. There we go. Okay, oxidation states first. 2 plus and 0. Easy. This one, 1 minus. This one is minus 2 there times 4 is minus 8. Hold 1 out. Minus 7 needs to be balanced. That means plus 7 here. Okay? So now we can decide which one's reduction and which one's oxidation. So the reduction reaction is which one? Which one is reduced? Go from here to here, plus 7 to 2 plus. That's a decrease in oxidation state, which means we have to add 5 electrons. Add 5 negatives to that, you get a 2 plus. So the reduction reaction is this one. And I'm going to put this here just as a reminder. And leave some room. And now this one's going to be manganese 2 plus. I'm going to leave out the states because it just clutters things up. Okay, how about the oxidation? Well, the only thing left is bromine to bromine. So this minus 1 lost electrons to go to a plus, to go to a 0. I had to lose 1 electron. So now we've got this one, and it yields that one. Okay, first things first, balance the elements, except oxygen and hydrogen. So there's 1 manganese, there's 1 manganese, there's 1 bromine. There are 2 bromines. We need 2. Okay? Now we balance the oxygens. There are no oxygens here. We're done with this one. Oxygen here. So where does the oxygen go that balances that? All right? Goes on this side. As water. So we have 4 oxygens. We need 4 oxygens. Correct? Now we've got 8 hydrogens. Okay? That one's good, that one's good. So now we do electrons. We're going from plus 7 to 2 plus. We need to add 5 electrons. And for this one, we lost an electron for each bromine, right? Went from minus 1 to 0. But now we have 2. There you go. So now, before we can put them back together, the number of electrons have to be equal. So what's the best way to do that? We've got a prime number 5 here and a prime number 2 there. We can't multiply 1 times a number and get them to balance. Well, we could multiply this one by 5 halves, and that would be 5 here. But we want whole number multiples in the end anyway. So the method that works the best for me is if you have an odd and an even, is to cross multiply. In other words, take that 2 times this one, and that 5 times this one. So we would do this. A 2 here, and a 5 there. Okay? So that means we have 2 manganate plus 16 hydrogen plus 10 electrons, and 2 manganese 2 plus, and 8 water. Okay? And this one would be 10 bromines and 5 there and 10 electrons. Okay, now we can add this one and this one together. Okay, so I'm going to take these two, I'm going to put it right up here underneath that one. So we got 2. I better start over here. We've got 2 manganates plus 10 bromides plus 16 hydrogens plus 10 electrons. We got 1, 2, 3, 4. 1, 2, 3, 4. And on this side, we've got these 2 manganese 2 plus and 5 bromines plus 8 water plus 10 electrons. Okay, that's 1, 2, 3, 4. 1, 2, 3, 4. Okay, that's our combined equation. Now, let me make some room so I can finish this out. There we go. Okay, what can we cancel? Well, let's see, 10 electrons definitely. How about, this is a 16, right? Let's see. No, can't cancel that, can't cancel that. Hydrogens, that's it. We've only got water on one side. So our equation is 2 MnO4 minus plus 10 bromides plus 16 hydrogens yields 2 manganese 2 plus plus 5 bromine plus 8 water. That's our balanced equation. We know the electrons balance because we just canceled them. How about the elements? 2 manganese, 2 manganese. 8 oxygens, 8 oxygens. 10 bromides. 2 times 5 is 10 bromines. 16 hydrogens. 2 times 8 is 16 hydrogens. We're good. That's balanced. And here it is in animated PowerPoint form. One slide after another, doing the same thing I did on the board. Well, actually, it's a little different order. I need to look into that and fix the slides so that they're consistent. There we go. All right. That's it. There's your balanced equation. Now, the key to working the half reaction is to be extremely methodical, fastidious about the details. The procedure does work, but it only works if you do it step by step, constantly checking yourself to be sure that you haven't made some error somewhere, like I frequently do and have demonstrated in this class. All right, let's see. Now, we've got this equation, and that is balanced for acidic solutions. What if the solution needs to be basic? Okay, we use my fake acid method. You do the acid balancing first. Then you take the balanced acid equation and you neutralize all your hydrogens. How do you do that? If you've got to balance this many hydrogens, then you need to add hydroxyls on both sides. Okay. How many hydroxyls does it take to balance that many? 16, right? Right? 16 negatives, 16 positives. So what does that give you? That gives you hydrogen, and hydroxyl always makes water. 16 water. So we have 16 here. We need 16 hydroxyls there. Right? So we're adding 16 hydroxyls there. We're adding 16 waters here. Okay? Now what do we have? Well, now we have 2 MnO4 minus plus 10 bromides plus 16 water yields 2 manganese plus 5 bromine plus 8 water plus 16 hydroxyls. Okay. Now you do like before, you cancel common terms on both sides. So we got 16 waters here and 8 there. So those 8 are gone, and this becomes 8. Right? 8 of those are taken up here. Hydroxyls, they're none to balance, so that's it. It's manganate plus 10, 2 manganates plus 10 bromides plus 8 water yield 2 manganese 2 plus ion plus 5 bromine, elemental bromine, plus 16 hydroxyls. That says this is a basic solution. And that's what this animation should show. Right? 16 hydroxyls go on both sides. Right? You can't create matter, you can't destroy matter. So if you add it on one side, you got to add it on the other side. Here we go. All right. All right. Now we'll cancel common terms. There we go. And that was your balanced equation, just like I showed you here. All right. Now, that was redox reactions and balancing equations by the method of half reactions. Now we're actually going to talk about electrochemistry. So in electrochemistry, we focus our attention now on the exchange of one form of energy into another. In this case, chemical energy and electrical energy. And it makes sense. If electrons are moving, then there should be some energy there that could be tapped. Remember the conservation of energy. The total amount of energy in the universe is constant. In other words, you can't create energy, you can't destroy energy, you can only transform it. Now, from a chemical standpoint, that is true. Similarly, the conservation of mass, of matter. You can't create matter, you can't destroy matter, you only change its form. And for chemistry, that's good. It works. Of course, when you get into nuclear physics, then Einstein steps in with his equation, E equals mc squared, and you know that energy and matter are interchangeable. But for chemistry, we're not interested in that. Chemistry, we can use conservation of energy and conservation of mass without any fear of one stepping on the toes of the other. So what we want to do is look at the interchange of chemical and electrical energy. We have shown by balancing those equations that there is a transfer of electrons when you have a redox reaction, right? But those electrons in our previous examples, they transferred within the reaction medium. In other words, we have no access to those electrons when they move. So we have two types of processes in electrochemistry that we're interested in. One is the reverse of the other. The first one is we can produce an electric current from a chemical reaction, but we have to do it a special way, right? We can't put those reactions together. The two half reactions that we use to balance the equation, if you put those two reactions together in the same vessel, then there's no way that you can tap those moving electrons. But if we separate the half reactions into separate vessels and provide a way for the electrons to move externally, then when that electron is moving in that conductor over to the other vessel, the other half reaction, we can tap it on its way and extract energy from it. And that's what we mean here by production of electric current in an external circuit. Now, if we run that's for a reaction that runs spontaneously. In other words, no intervention. You put them together, they react. If you want to run that reaction backwards, then you need a source of power to couple to that reaction to force it to go backwards. Right? So that's why I said one is the reverse of the other. This is the spontaneous one. This is the non-spontaneous one, requiring external intervention to make it run. So the first type, the spontaneous type, we call electrochemical cell. And here's one possible reaction. We get the manganese going from manganese 7, right? 7 plus to manganese 2 plus, right? That's one half reaction. And there's the other half reaction, right? We split them apart already. So what if we put one in one vessel and one in the other? So one vessel is a half cell and the other is the other half cell. So in this half cell, what's going to happen? Well, in order for that reaction to happen, going from here to here, this manganese has to acquire 5 electrons per manganese. Where do those electrons come from? They can't come from this solution anymore over here, but they can come from the wire. So the electrons are going to travel through this wire and come out over here, right, and react with that manganese 7 oxide. So what's happening in this cell? There's reduction going on here. Those electrons are being supplied here to reduce that manganese. And they're being supplied by the oxidizing agent in the other cell. Iron is being oxidized to iron 3+, iron 2+ to iron 3+. So it's delivering those electrons here. It's losing the electrons in the process, but they're being delivered through the wire to the other cell. Okay? All right. If we go this route, right, what we are tending to do is build up a negative charge on this side, right? Electrons transferring over here builds up a negative charge, and it builds up a positive charge on this side. And natural processes tend not to go very well when you do that, because you've got a driving force that's pushing the electrons backwards, right? They repel each other. So the more electrons you put over here, the more repulsion there is, and they tend to resist the flow of electrons into that solution. All right, so we can't allow that to happen. We've got to provide a way to balance the charges. So we have to connect these two solutions somehow, so that we can get an ion exchange and rebalance the electrons. So we do it by creating a circuit. In physics, no electron flows without a circuit. No charge moves without a circuit. Circuit comes from the same root word as circle, right? It's complete all the way around. So to complete the circle, we need something over here, right, independent of this electron movement, to rebalance the electrons. So the negative ions on this side can move to that side, and the positive can move to this side to rebalance. So we do that one of two different ways. You can either do it with a salt bridge, right? A soluble salt in this tube will allow anions and cations to move and rebalance charges. Right? So you need a plug here, because you don't want complete mixing, right? That would mess up your reaction mechanism. So this salt bridge is usually has a porous plug in the end, and or you can mix your salt in with a matrix that holds it in place. You could use a gelatin. Well, actually, gelatin's not a good option. I've done that before, and the gelatin actually participates in the reactions, which messes with your measurements. So a better choice is a non-ionic thickening agent like agar. Right? Anybody who's had microbiology or a general biology course in which you use petri dishes, or you could use test tubes with slants built into them, right? You let them pour the agar in, and you tilt the tube so that the agar tends to lay at an angle. And then when you solidifies and you straighten it up, you have a slant. Or you can use a petri dish. So that agar medium, the agar is the thickening agent. We use it in chemistry too. You just mix in your salt with the agar, and then when it solidifies, it's not going anywhere. The other possibility, which is actually more efficient, is to put a porous disc between the two. Now the porous disc simply keeps this reaction medium separate from that reaction medium, and the pores are only allow ions to move. Small ions at that. So now you have a circuit, right? The electrons move and the charges move all the way completely around the circuit. And you can measure a voltage from your cell, your electrochemical cell, by connecting these two half cells. Another term for the electrochemical cell is a battery. And then the giving credit to the inventor of the battery is, I forget the man's first name. He was Italian. His last name is Galvani. So we call it the Galvanic Cell, which is another name for a battery. So when that happens, under the right conditions, we can transfer electrons from this side that's being oxidized to this side that's being reduced. You know, we have special names. This side, excuse me, where reduction takes place is called the cathode. And this side where oxidation is taking place is called the anode. Now the way I get that solidified in my brain is to look at it this way. If you have this one connected to this one with a porous disc, right, and you have this electrode there, and your electrons are moving this direction, and this is the cathode. Well, actually, the cathode is actually this whole thing is a cathode, and this is the anode. This is the site of reduction. So when these electrons arrive over here, they're added to something, and they decrease its oxidation number, its oxidation state, by adding electrons. That is reduction. Over here, the electrons are being lost, right? So they're moving that way. So you have oxidation on this side. Okay. So the way I rationalize so that I don't get them mixed up is the cathode is the place to which cations migrate. So if you've got any cations in here, they're going to be attracted to those electrons to be reduced. Okay? So the cations move to the electrode in a cathode, in the half cell for the cathode. And then the other one's the anode. But by definition, the cathode is where reduction takes place. Actually, I was right the first time. That is the cathode, and this is the anode. This is the reduction half cell. This is the oxidation half cell. Okay, so now that we have those definitions in mind, I would like to make one more point. The way this is shown, this diagram, the cathode is here. And that's true. That is where the reduction takes place, because at the very exit of electrons from this strip of metal, in this case, then there will be reduction take place immediately. But suppose the half reaction in this side, the reduction reaction, occurs entirely in solution. Then what do? Then all you need is some way to deliver those electrons to the solution. And in that case, this could be some inert metal like platinum that does not participate in the reaction. Or it's even cheaper if you use a graphite rod, which will also conduct electricity. It will deliver the electrons into the solution, but it doesn't participate. So that's a possibility. When you put these two half cells together, it's entirely possible that these electrodes do not participate in the reactions. Sometimes they do, sometimes they don't. What's important is, what is the reduction reaction over here? What is the oxidation reaction over here? All right. So now, if we reverse the process, we get electrolysis. That's where electrical energy is used to produce a chemical change, rather than the chemical change producing the movement of electrons. Okay, this is non-spontaneous. So you have to add an external source of electricity in order to make it happen. It's like running a galvanic cell in reverse. By the way, if we do that, let's go back. If this is the cathode for a battery, a galvanic cell, if we run it in reverse, now where's the cathode? If the electrons are moving backwards because we put a source up here to drive them that way, now the anode becomes the cathode, and the cathode becomes the anode. All right? Just the definition. The cathode is where reduction takes place. So if we reverse the flow, now the cathode is over here. Okay. Examples. Chrome plating a bumper. Now, that's not done much anymore on new vehicles that are produced. They're all plastic bumpers that may have a metallic superstructure in them with hydraulic pistons to absorb the impact. But at one time, all cars had solid bumpers that were bolted to the frame. So when you smacked into something, the energy of that collision was delivered to the entire structure of the car. Now, in earlier days, the mass of the car was sufficient to absorb that shock. And the bumpers were probably 1/4 to 3/8 of an inch thick metal. They were heavy duty, but they were made out of steel. And in order to prevent rusting, you would plate them in chrome. And it'd also make them shine. But that chrome protected them, and it gave a nice look. And antique cars, you can still get that done. You can have the bumpers chrome plated. Say if the bumper is old and corroded, and or if it gets scratched or something, you can have it replated. But that process is electrolysis. We're running an electrochemical cell in reverse in order to deposit chromium metal on the surface of the bumper. Okay, that's all we're going to say about that, because in this course we really don't have time to go into details. Let's go back to batteries now for a second. Different types of batteries. For the longest time, the only kind of battery that you would find in common public use, particularly in vehicles, is the lead storage battery. It's that thing in one corner under the hood of your car, and you try to pick it up, you know it's very heavy because it's made out of lead. Well, the reaction that takes place in there delivers 12 volts on most cars And for many diesel vehicles, it may be 24 volts, or on tractors, it may be 24 or even 48 volts. And I'll show you how that happens. But the reaction, the chemical reaction, is exactly the same for every one. Now there's competition from lithium ion batteries now in some electrical vehicles. And they're used because they're much lighter than lead storage batteries. And weight is an issue when you're trying to drive your vehicle with solely on electric charge. But the reactions for the lead storage battery are here, the two half reactions. The oxidation reaction takes lead metal and converts it into lead sulfate. And we know from our solubility chart that lead sulfate is insoluble in aqueous solution. So when this reaction occurs on the lead plate in your battery, it builds up a lead sulfate layer on that plate as it converts lead into lead sulfate. And on the other plate, the cathode, we have lead oxide. So we have two types of plates in there. The anode is made out of lead, the cathode is made out of lead oxide. And the lead oxide undergoes, the lead in the lead oxide undergoes reduction. It's converted from lead 4 plus to lead 2 plus by adding electrons. Right? And this all occurs in acidic solution. So that occurs at the cathode. And it also deposits lead sulfate, lead 2 sulfate on the plate. Okay? So we tap into those moving electrons in an external circuit. But notice that the product of each reaction is the same on both sides. For this oxidation, you end up with lead sulfate. For this reduction, you end up with lead sulfate. And also, these plates are submerged in the exact same solution, sulfuric acid, sulfuric acid. So what does that mean? That means that we don't need a porous disc or a salt bridge, right? The separation occurs at the plates. They have a common solution between them, which naturally reduces the complexity of the lead storage battery. Now, there's some lead storage batteries. It used to be that your battery under the hood of your car had to be vented, had little holes in it to release gas. The gas that it released was hydrogen. As you recharge the battery, you run the reaction backwards here. You turn that lead sulfate back into lead oxide, and you turn this lead sulfate back into lead. And if you go too far, and even if you don't go too far, some of that hydrogen that you produce in the process is converted into hydrogen gas. And if that collects in your battery, then eventually it can explode. Builds up pressure, if nothing else. So now we have lead storage batteries that are sealed to keep the sulfuric acid from corroding everything. And they do that by providing in the battery itself an absorber for hydrogen gas. So if the hydrogen gas is produced, it is absorbed into that matrix until you start the cycle again as a battery, and then you consume that hydrogen in a secondary reaction that's not shown here. But that's how you can seal a lead acid battery and use it in other applications besides under the hood of your car. If you have an uninterruptible power supply connected to your computer, it will have built into it a sealed lead acid battery. That's why they're so heavy. and it uses that technology to absorb the hydrogen to make it safe to use in your house. Okay, so that's your lead storage battery. There's the overall reaction, right? And notice that, well, what happens, a lead storage battery will undergo many cycles of discharge and recharge. But as you do that, some of that lead sulfate remains on the plates and is not converted back into lead or lead oxide. It's just the nature, that's the mechanics of the battery. So over time, that lead sulfate tends to build up on the plates. And when it builds up to a high enough level, it actually occludes the surface of the plate. So now the solution can't get to the underlying plate, and you cannot complete the reactions, the half reactions, to recharge your battery. Under those circumstances, your battery is dead, and it's also called sulfated out. And the reason it's called sulfated out is this lead sulfate covers the plates. They're not usable. The only way that they can be restored is to send your battery back to a recycling service, and they will perform the chemistries required to restore the batteries. Okay, I've already said this. There's no need for a salt bridge or a porous membrane because all the plates are submerged in exactly the same solution. Now, this shows them all together, right, in the same container. What you do have to do is, if you have more than one cell in your battery, those cells have to be separated. Right? This is a single cell, and it will produce a voltage of 2 volts when it's new. So how do we get 12 volts out of a battery under your hood? Well, there's a law in physics that says that the total voltage that you get from a battery is equal to the summation of the individual voltage of the cells. So you have voltage 1, voltage 2, voltage 3, on out. So what do? Well, in order to do this, this has to be in series, which means if you have a battery here with a plus here and a minus here, then you need another battery here with a plus here and a minus here. Those are your electrodes. So you connect them in series, like that. And then the voltage you measure here is the total of those. They have to be connected in series, plus to minus, minus plus. So how many would it take in a lead acid battery under the hood of your car to make a 12 volt? Well, if they're 2 volts each, then you need 6 of them. You need 6 individual cells that are physically separated in that battery, that are connected in series. You don't see that because it's underneath in the mechanism of the battery. All you see is these N positive and negative poles. Okay. So when you recharge the battery, you're actually converting it into an electrochemical cell, right? The alternator under the hood connected to your engine is supplying electrons to the reaction so it runs in reverse. So I just mentioned something without defining it. The voltage, which is called electrical potential. You can think of voltage as a pressure, a push. That push driving the electrons forward from one side to the other. And they always flow from the anode to the cathode. Right? So if the electrons are flowing from the anode to the cathode, which one of these is the anode and which one's the cathode? This is the anode. It's the negative terminal, which means electrons are coming out. And this one is the cathode. And similarly, that's a cathode, anode, cathode, anode. That pressure that we talk about, the push, is measured in volts. This is electrical potential. So batteries that you put in your flashlight, they produce, when they're brand new, they produce a minimum of 1.5 volts. That's their rating. But if you put a meter on them and measure it, you'll find that they're usually 1.65 volts. So they're greater than 1.5. When they're discharged, when they can't light your flashlight anymore, they'll be maybe 1 volt or less than a volt. So there you go. This is the simple statement for what I just showed you here for your lead storage battery. There are other types of batteries. They're called dry cells, right? That's the D size, the C size, the AA's and AAA's that you can buy in the store and run your calculator. Now, calculators don't use that usually. Various devices, including flashlights. You can use these dry cells. Well, why are they called dry cells? Because the electrolyte, which is the medium in that half cell, sulfuric acid for the lead acid battery, that electrolyte is not liquid. It still has mobile ions in it, and it still has the reactants in it, but they've been stabilized by some type of non-reactive gel, and that makes them safer, right? If they're not liquid in there, then if you poke a hole in it, then the liquid won't squirt out. There are different types. There are those that occur in acid solution, like we balanced earlier. This is one example. So zinc is converted to zinc 2+ and delivers those electrons from the anode. And then in the matrix of the battery, you have ammonia and manganese oxide, and they are receiving the electrons. The manganese is receiving electrons to be reduced at the cathode. And now that was the acid version. The alkaline version takes this zinc and converts it to zinc zero oxidation state to 2+. So it's, again, the anode. In this case, we're just taking the manganese here and making this manganese. So the reaction is essentially the same. Let's see if I'm correct on that. We're going from zinc, yes, zinc to zinc 2+, and we're going from manganese here, yes, same. But the environment is slightly different. But the oxidation reduction reaction itself, at the most basic level, is the same. It's occurring in a different environment. In this case, it's alkaline. And most of the dry cells that you buy off the store shelf are the alkaline version. So how is this battery built? Well, it's very compact. You have this outer shroud of plastic that prevents electric shock or transfer of electrons through alternate pathways that you don't want. But the inner mechanism is the anode is actually the casing of the battery. Right? The anode is this zinc casing. And then it reacts with this matrix in here where the manganese is located. All right. So in that case, you don't need a salt bridge or any type of other separator, because this is fixed in its matrix. It's kind of like a my mind's gone blank. It's not a solution, but it's sort of a mixture of a solution and a solid matrix. It's right on the tip of my tongue. Colloid. Forms a colloid. But the reaction in the cathode here does not react with this conductor, right? The cathode reaction occurs in the paste. So you need something to conduct the electrons from one side to the other, externally. And they use this graphite rod as the cathode. Like I mentioned earlier, of course, you could use platinum, but that would be a very expensive battery. So graphite is a better choice. So the cathode, the connector on this side, where the electrons are delivered, is on the top of the battery, and where the electrons are externally, they're sent out of the let's see. Hold on a second. Yeah, that's right. So this cathode is what receives the electrons, and the anode down here at the bottom, the side that you put against the spring, right? When you stick it in the device, that's the side that goes against the compression spring. That's the anode side. That's where electrons are delivered. They come out there. Okay. And this just emphasizes the point that that graphite rod does not participate in the reaction. It only serves as a contact point for transferring electrons. All right. Now let me see. Let me move on my hard copy. Okay, just 2 or 3 more slides, and we'll be done. Again, these dry cells don't contain a liquid electrolyte. It's been stabilized with some sort of matrix, like our auger. There are other types, and these are similarly stabilized with that solid matrix. The silver cell uses zinc as the anode, so that's where oxidation occurs. Right? Zinc will be converted to probably zinc 2+, more than likely. And then at the cathode, we have silver oxide here, and it will be reduced to probably silver metal. Those cells are not used much anymore. They should be kind of expensive, actually, because of the silver content. Mercury cells, you almost never see them anymore, simply because they have mercury in them. They're hazardous. And if you just throw them in the trash, you don't recycle them properly, they end up in the municipal dump and over time contaminate that site. But you see a similar arrangement here. There's your cathode with the mercury oxide matrix here. You would have a similar arrangement for the silver cell. Instead of mercury here, you would have the silver oxide in here. And then you would have zinc as this cell, this casing. And they would be separated here by this insulator so that you don't get transfer of electrons by an alternate route. We would call a short. That would be a short circuit. Another type is the nickel-cadmium battery. Right? It's rechargeable. The problem with nickel-cadmium batteries, and I don't think I have the reaction listed here, so it's not important. You can look it up. It's freely available. The nickel-cadmium batteries, I used to have one in a trimmer. Right? And what I noticed, which I already knew beforehand, but I was expecting it, was that as you use a nickel-cadmium battery, if you don't discharge it all the way down to 0, where it will not function anymore, and then recharge it, it has memory. In other words, if you only partially recharge it, partially discharge and then recharge, it thinks that 0 volts is where you left it. And you lose all that other below, all that other potential. So that battery memory was always a problem with nickel cadmium. In addition to the cadmium, of course, would be considered a pollutant if you just threw them in your landfill. Nickel, not so much. It's not quite as toxic. Cadmium is. But that memory effect was really a problem. Now we have, and I don't think I have it included in this slide. These slides were developed before the advent of the lithium ion battery. One thing about lithium ion batteries is, besides they're very light, notice where lithium comes from, right? Right here, way up here, right? It's the third element in the periodic table. It's very light. So what that means is, and it's a small atom, a smaller ion, it takes up very less space. So you can pack a lot of it into a small volume, right? So what that translates into is energy density. Lithium ion batteries are more energy dense than most other batteries. But the lithium technology that's used now for those batteries is very sensitive to overcharging. So once it's discharged, it doesn't have the serious memory effect that the nickel cadmium does. But if you overcharge it, right, you're running it backwards like an electrolytic cell to recharge and add energy to it. If you can charge beyond, or in other words, you can force it into another reaction that's undesirable. And what can happen is, if you overcharge it, it will overheat and explode. So most lithium ion batteries are built with electronic circuitry into the mechanism, into the battery, that senses when the battery is fully charged and introduces a cutoff. It will not allow more electrons to come through and charge. It's a safety mechanism. But even with that, some lithium ion batteries will overheat and explode just spontaneously. That's why if you're going to transport them on an airplane or a train or a bus or through the mail, you have to declare the fact that lithium ion batteries are in that package. And they take special precautions when they transport them, so that if they do catch fire, they won't bring the plane down, or they won't derail a train, catch the train on fire, or whatever the case may be. Okay, so last topic is, actually there are 2 more slides. Corrosion. What is corrosion? We normally think, or typically think of corrosion as something like rusting. Rusting is corrosion. It's a special type of corrosion. Corrosion, in general, refers to the oxidation of metals to form some other compound, right, like oxides or sulfides. And in the process, the metal is oxidized. In other words, it becomes a reducing agent. Right? The metal would go, in our previous example, say, let's see. If we went from iron at 0 oxidation state, and we went to Fe3+, that would be an oxidation. And we would have 3 electrons over there. Well, how does it get to that? Well, usually you combine it with oxygen. Right? So you would say this one, that's a half reaction. Let's see, the other half reaction would be what? Oxygen then would be converted to, it would be reduced to something like water. That would reduce it, right? 2-. But also, this oxygen combines with iron, and it would produce this one, Fe2O3. That is rust. Rusting is a special case of corrosion. Any metal can corrode. All it has to do is react with oxygen, or it could react with sulfur, form a sulfide. Now, that's undesirable, right? We like metals for what they can do, like iron. As iron or as steel or as various alloys is a very useful element in its metallic form. We don't want it to convert to rust. I don't know if I've told this story before in this class, but there used to be a building in Atlanta, Georgia, where I lived, where I grew up, called the Omni. And it was built for sports. It was a sports arena, an indoor sports arena. So they would have basketball games. They would have hockey. Believe it or not, Atlanta had a hockey team. And the architect that designed the building wanted to use a special form of iron in the cladding around the building that would rust very quickly. It would convert to rust quickly, and it would turn the building red. What he was hoping was when you create this oxide layer, the Fe2O3 layer on the surface of the metal, it protects the metal from further oxygen and water getting through to the underlying metal and stops it from degrading. Okay, it was a good idea. We observe that with some metals do it just naturally, like chromium or aluminum. They oxidize so quickly at their surface that they protect the underlying metal from oxidizing. That's what we're referencing here. Some metals like aluminum, chromium, even zinc, protect themselves by forming that oxide layer. Well, the problem is, or the problem was, as this building, they built it, and as this building began to rust and produce that deep brick red color, it was pretty at first, but Atlanta gets a lot of rain at certain times of the year, and what it would do was it would wash that iron oxide off the surface. Some of it would be washed down onto the concrete pavement around the building, and you would have rust streaks running across the concrete. It was really ugly. They eventually tore that building down. Okay, so how can we use this oxide forming process to protect the underlying metal? Well, you know, and the name of the man escapes me for now. but the original inventor of stainless steel combined iron and chromium in an alloy. And his original mixture was 35% chromium. So that'd be 65%, about 65% iron, but it was a steel, right? So there might have been maybe a 0.5% or less of carbon, okay, to make the steel. You have to have the carbon to make a steel. Well, what would happen was the chromium was in sufficient supply at the surface of the metal that it would, and chromium is extremely reactive with oxygen. It forms chromium oxide instantly. If you scratch stainless steel, you can still see the scratch, but it will not proceed to rust. It seals instantly. Or in my grandparents' time, instead of plastic buckets, they had galvanized buckets that they could leave outside, and the bucket would not rust as long as you did not scratch the surface. Galvanizing takes steel, the steel bucket, and coats it with a layer of zinc. They just take the bucket and dip it in molten zinc. And the zinc, like chromium, is very reactive, and it forms that protective layer. In fact, it does, what this is showing you here, the buried iron pipe connected to magnesium, protects the pipe. Right, there's your coatings, there's the alloys that I talked, and there's the cathodic protection. That's what a galvanized bucket does. We still galvanize nails, right? Nails that are going to be used in exterior application, you'll see them have this kind of a dull look to them. And that's because they're coated in zinc. When you drive that nail into a deck, say, it's exposed to the elements, but it doesn't rust because the zinc protects it. The zinc, rather than the iron being oxidized, the zinc is oxidized in its place. And oxidizing the zinc supplies electrons to the underlying metal. Right? You want to keep that metal reduced. And that's what this magnesium is doing. As the magnesium corrodes, it oxidizes, and when it oxidizes, it releases, this is the anode now, it releases electrons through that wire to the buried pipe and provides electrons to the buried pipe so that it remains reduced. Okay, so that's one way to protect a metal. You sacrifice one to protect the other one. Now, in order for this to work, that metal, that magnesium, must be more reactive than the iron. Otherwise, the iron will react and maintain this metal in the reduced state. It will go the wrong direction, right? And we have lists of electrical potential for the various types of half reactions that these metals undergo. We call it a reduction potential table, but we're not going to deal with that in this class. But just to say that this metal needs to be more reactive than the one you want to protect. Now, another application that I don't see here, okay, for this cathodic protection, which part is the cathode? Well, the buried pipe is the cathode. That's the site of reduction. And the magnesium is the anode. Okay, another application that I didn't put in the slide has to do with ocean-going vessels, large ships that are in salt water constantly. Salt water is more corroding than fresh water, simply because it has those ions available. And how do you protect your ship? Well, the way that ships are protected, one way that they're protected, of course, is painting. But all you have to do is get a little scratch and then you're done for. So what they do is they wrap the hull of the ship in a big, thick strip of zinc all the way around. And they paint over it. And that strip of zinc is connected to a power supply in the ship. When the power is cut off, then what the zinc can do is corrode and supply electrons to the hull of the ship, which is steel, and maintain the integrity of that steel, maintain it in its elemental state. And then when the ship gets power back, the power drives electrons into the hull and into the zinc and reduces both. If there's any corrosion in the hull or any corrosion in the zinc, it will reverse the process, just like we did before, and reestablish that pure zinc band. Sometimes ships have to power down, right? And that's when the zinc really does its work. But as long as there's power, then you can maintain the integrity of the hull and the zinc strip simply by trickling electric charge, negative charge, into the hull. Okay, last slide. So when we force current through a cell, we drive the reaction in reverse. And one of the ways to do that is to electrolyze water. Right? The spontaneous reaction for hydrogen and oxygen is to go from hydrogen gas and oxygen gas to water. And that's what we do, or what we used to do, what we're planning to do. We used to do it in the space shuttle. In the three main engines, they used liquid hydrogen, liquid oxygen as fuel and oxidizer respectively. And the way they produced the hydrogen and oxygen you need is by this process. You electrolyze water. You just take the water. Well, this is one of the ways you can do it. There are a number of other ways, which are more polluting, actually. But this way splits water into hydrogen and oxygen gas. And in fact, this is the way that submarines in our military produce oxygen for breathing. They can stay submerged indefinitely because they've got power, nuclear reactor power, and they've got plenty of water all around them. They just take that water, they remove the salts, right? They, by another process that I won't take time to describe here, and they take that pure water and then they electrolyze it, and it produces breathing oxygen. And then, of course, they have to remove the carbon dioxide from everybody exhaling. So there's another technology for that, but they have all the oxygen they need by this process. Now, if you have this hydrogen and oxygen available, you can put them back together in what we call a fuel cell. It's a type of battery. And when this reaction occurs, you can extract a current from it. Electrical power. In fact, the Apollo program, in fact, definitely the Apollo program, where we sent astronauts to the moon, used fuel cells to provide power. They had big tanks of hydrogen and oxygen in there for storage, and then they combined them in fuel cells and made all the power they needed. That's why, watch that movie, Apollo 13. What happened there was an oxygen tank exploded by faulty manufacturing. And the astronauts could very well have died in space. because they lost the power that they needed to operate the equipment. Not to mention the oxygen that they would use to breathe. Okay, so this is the same reaction that I mentioned earlier. Actually, I didn't mention it specifically. I inferred that hydrogen gas could be produced. But if you overcharge a lead acid battery, where's that extra charge going? Well, the extra charge can go into the water that's in the acid solution and produce hydrogen gas. And there's oxygen there too. So once you build up a certain concentration of oxygen and hydrogen, they will spontaneously react. And that's when your battery explodes. So you need a mechanism to control that. And by the way, if we could do two things: produce an unlimited source of non-polluting power, right? Nuclear power is a good place to start. Fission, right? Uranium as the fuel, would produce unlimited amounts of electricity. But even better than that would be fusion, where we could take hydrogen that there's plenty of it on planet Earth, and fuse them together to make helium and produce lots of power, enormous amounts of power. That power could be used to split water into hydrogen and oxygen. And then we could run all our vehicles on hydrogen for pennies. Just build the fuel cells, and that's another technology that has to be perfected. Build the fuel cells into our cars, and then all you'd have to do is fill up with hydrogen. That's why I call it the holy grail of the non-polluting economy. For now, we're stuck with fossil fuels. No matter what the people in power now say, that we have to stop using fossil fuels. Well, in the first place, that's not going to get us where we need to be. In other words, global warming or global climate change is not as serious as they say it is. Plus, that change that they want to make will not fix the problem, because most of the climate change is occurring external to the Earth. It's coming from the sun. So we can't fix it that way. Plus, if we do away with fossil fuels now, the world economy will collapse. And if you think things are bad in Bangladesh or sub-Saharan Africa, you'll see the entire world go into that type of economy if you do away with fossil fuels. That's not a belief, that's a fact. It will happen. So the moral of that story is the world needs West Virginia coal, to make a long story short. But if in the meantime we can develop a sustainable hydrogen economy, then this would be the route that we would go. We would just convert water into hydrogen and oxygen, and then run all our vehicles, our industry, on hydrogen. Of course, that would require a massive change in our infrastructure, because our infrastructure now is based on delivering for our cars gasoline. Right? We would have to change it to hydrogen. Okay, so I've been on my soapbox long enough, and that's the last slide for this discussion. So since I'm all alone, that's the end of chapter 18, and we'll follow up. This is, what is this, Thursday? Thursday. We'll follow up with Tuesday and do a review, and then I'll decide then if we need to do 2 reviews. We could do send gauge one day and review document the next day, so that we can be on schedule for the last exam here. Then there will be a final exam, and we'll need to do some review for that also. Okay, that's it. Time's up. Right on time, 11:59.